So yet another important point, because shape is an abstract class, although it can have its own data members and its own, I can say here, implementation. It behaves totally like a normal class, right? But because we decided that it does have some abstract operations, which are pure declarations of the interface, essentially a promise that we will, we will deliver it, right? Because it's an abstract class, since it contains abstract operations which are not defined in this class, this is not possible. You cannot say shape ch equals new shape. You cannot do this. Let me save it, and let me try to compile it. Where's my clean build, I guess. So the compiler error is shape is abstract, cannot be instantiated. So this line right here is not going to compile, because the compiler says you cannot say new shape. Well, you may say, well, how come? Look, we had the whole array of shapes and it was okay, so what really is going on? Well, look, when we created an array, we never created any shapes. Remember, to begin with, this array of shapes was initialized with zeros internally, with like null pointers to non-existing objects. But then we said shape 0, 1, and 2 and assigned a particular references to already existing objects, or actually created a new one on the fly. To this point, if you examine this demo code, there was not a single time when we said new shape. This one doesn't count, because when we say new shape and indicate square brackets, it's the new array object is created. So no shapes are created, but this array object, like a collection, is created. And collection in Java is also an object of its own type. This is what you cannot do with abstract class. You cannot create new shape as is. However, you can create new circle, and that's okay. Circle is a shape, right? And so from this point on, once you create new circle, but if you're using a reference type shape, there is no way for you directly at this point, well, at least at this very basic level, to tell the rest of the program that this ch is actually pointing to a circle. The rest of the program will say, I'm dealing with a shape, and because shape is an abstract class, and I have a reference to some object, all I can do is basically you call this method, right? That's all I can do. The rest of the program will be able to do something like that, just to call shape draw, but nothing else. Because shape is an abstract, it cannot be instantiated, but any derived class can be instantiated, right? So I could do that. Again, on the next line, I could say shape equals new rectangle. A new rectangle, and specify, its sides, whatever. So what happens to this circle when I do new rectangle? Well, my code has no longer any connections to this particular instance, and guess what? Every object in Java counts how many references outstanding exist to its instance, and if that count of references goes to 0, the object is marked for deletion. A separate thread in Java Virtual Machine, which runs in parallel with your program, at some point will revisit all objects that have a reference count 0, will mark them for deletion, and eventually they will be the memory allocated by these objects when I cross it out, really nothing happens, but the memory again becomes available to the system, so that we don't leak this memory, we do not waste this memory, we give it back to the system. And that's what Java does automatically. After we say new, for a while we'll be using those objects. Eventually all objects are going away, because once the program ends, all reference counts go to 0, and each object is getting marked for deletion, and Java Virtual Machine itself may be exiting, and that's a whole different story. But if it doesn't exit, then it will be eventually collecting these objects and marking memory allocated by them as again available. So next time you create new object, it may as well be placed in this particular spot in memory. Okay, so that is the nature of new. The situation is completely different for a C++ programmer, because in C++ you have to choose a strategy, what to do with your objects, because there you're also responsible as a programmer for deletion of your objects. In C++ you have to delete your objects. As you can create them dynamically, you have to find a way and proper time and proper place, or choose a proper container, so that somehow the object will be deleted. Otherwise, there is a memory leak. This is less important for programs with just like run at the console, like start and exit, all memory is returned back to the system. But if you're running some sort of a service that runs in the background and continuously staying alive, it's a huge problem if you just say new all the time and never delete your objects, because you will be leaking memory. The memory will be allocated by you, but never returned back to the system. So, and over decades of its evolution, C++ of course now has features that are very similar to automatic deletion by Java, but again, it's your choice which way to go in C++. In Java, garbage collection is part of your life, and as soon as no one has access to your object, the object will be deleted. It's good to know, and it's a great convenience. And it's also adds to the safety when you program, for example, on embedded devices. On embedded devices, if your embedded device supports Java Virtual Machine, and you're programming there, it also is a big benefit in terms of the safety in multi-threaded environments and many others. Having automatic garbage collection is a great thing to have. In C++, you can actually add automatic garbage collection also to your code by including a set of headers that implements automatic garbage collection. So more things are possible in that environment. Here, objects are safely deleted automatically by the environment. You don't have to worry about deletion of your objects. So that's good news for a Java programming. Any questions about this? Well, let's see. So polymorphism is basically the principle of using a particular interface, first defining this interface like we did with our shape class, and then using it. But the outcome of its use is that each time you use it, the objects that are being referenced will provide their own implementation of the method which we're trying to call. That's all. That's just we say it's polymorphism or polymorphic behavior. It's also called dynamic polymorphism, to be complete, because this polymorphism happens at runtime, right? Because when the compiler compiles your program right here, when I say shapes with index such and such draw, or create a loop which basically goes through the entire array of shapes that I have, and each single one of them says draw. When it at compile time, when the compiler compiles your program, it doesn't know which objects will be populated there. It really doesn't know. It has to make that decision at runtime. Well, fortunately, it's a very fast decision, and it doesn't really take much of the execution time from the program, so it's very efficient. In fact, in Java, all methods are polymorphic. All methods are naturally virtual. They can be made non-virtual or but with the default setting, Java provides this behavior by default for every method. So there's there's never a difficulty to add methods such as draw to your classes, organize them in a hierarchy. But for the polymorphic behavior to be used by you, the programmer, you have to have some sort of like an abstract pointer or top of the hierarchy where you can create these objects, but remember the reference of this type. And through this variable of this top level type, you can then refer to each concrete type, and they will perfectly respond to your messages. This is polymorphism. This is polymorphic behavior. There is also compile time polymorphism, or also known as parametric polymorphism, in C++ implemented through templates of classes, in Java implemented through Java generics, right? So that will be the topic of our discussion towards the end of the semester in our Java class. So anyway, but dynamic polymorphism is very effective, and it's a very strong platform for which you can, expect at design time many different things to work very efficiently and in a very flexible manner. I mean, if this didn't exist, frankly, I don't know what I had, an alternative to draw. If polymorphism didn't exist, would be some crazy code, maybe like one single implementation of draw, which would, every time it's been called, would have to check what kind of object is this, do some other checks, create some messy things such as, do I have a radius, do I have a side, do I have two sides for the rectangle, and all in one place. Poor design, right? Simply because someone didn't know that they could use a polymorphic behavior and have a very clean implementation for each type of class that is, subclass from the superclass, using Java terms. Okay, so it's very effective. Otherwise, it would be really problematic to write this program. I'd still be writing it. I'd still be making some workaround decisions in terms of how do I deal with, in every single situation, how do I deal with my shapes. Also, look, what else is possible is this. Right? So I can quickly add other methods which are abstract, go ahead into each single class and implement them. Oh, I know how to compute the area of a circle, square, rectangle. And so this becomes a very clean way to extend the functionality of already existing classes, right?